Okay, I'll get this thing moving. Yeah, really pleased to present Graeme Woodward from WRC, so thanks very much, Wireless Research Centre. It's a really fascinating topic, so thanks again.
Thank you, Chris. So I'm going to expand upon a presentation I gave last week at the New Zealand Wireless Workshop, and I'm going to sort of cover a lot of the stuff we're doing at the Wireless Research Centre that relates to drones. I don't know whether all of you realise, but a couple of years ago the university invested, had a CAPEX grant, college-wide CAPEX grant to invest in a bunch of drones, bought 9 drones. They're owned effectively by 4 departments, EC is one of them. We keep half of them in Wireless Research Centre, the other half kept up in Erskine. So yeah, they're a college resource, so if you have work you want to do, particularly on collaboration and swarming drones, that's they're there. But so I'm going to motivate the talk today by making the claim that one day a drone may save your life. This is the UC Drone Lab, which is all about swarming UAV research, cross-departmental. So there's a bunch of different topics that we're interested in, such as autonomous 3D navigation, mapping, so reconstruction from images collected from drones, classification, recognition, swarming models, sense and avoid. That's a major enabler for use of drones by industry, is their integration into the airspace. So one of the most basic things they need to be able to do is sense another aircraft and avoid it. And do that in a very fail-safe way. Autonomous takeoff and landing, distributed intelligence, ad hoc wireless comms, which is particularly of interest to us, and things like software practices for airworthiness. Again, that's another sort of enabler that the CIA would like to see before they, let everyone loose with drones in airspace along with manned aircraft. So we have 5 of these craft here. These are built by Aeronautics, which is a Kiwi company based up in Raglan. They're very much configured for research purposes. They have like an Intel NUC on there with an i7 processor, a large solid-state hard drive, various sensors, a downward-facing LiDAR. So they're highly reconfigurable and they get a lot of use in various projects. And so they're the ones that are kept in the John Britton building, and up in Erskine they have another 4 highly configurable machines which are a bit different to these by a German company. Some of the work I'm going to be presenting was done by a master's student, Zane Barker. Some of you guys may remember him. He was our undergraduate and then finished his master's with us just a couple of months ago. And the other thing I should point out is that we manage a flight test area, which is down at Birdlings Flat. It's 100 square kilometres of segregated airspace. When we enable it, we can, when we activate it, we can fly up to 1,000 feet altitude, and we are allowed to fly beyond visual line of sight in that space. Okay, so who needs drones anyway? And a few wireless examples. Object tracking. So this is looking at autonomous object tracking from 1 or more UAVs. We did this work for Scion. They were interested in understanding dispersal characteristics of insects. So it sounded a bit far out there when the Scion entomologist came and said, do you think we could have a drone chase insects about a forest? But actually we got surprisingly far with it. There were two basic methods being considered. Radio direction finding, so you steer and do the range finding using dual Yagi antennas. So Yagi antennas are just like the antennas you use to receive your TV. And this is here at Island Fields, 2 Yagi antennas on top of a UAV, separated by about 90 degrees. So I have there an antenna pattern for one, and if you put two of them on there at 90-degree separation, you can see that the different signal strength you receive, you can tell the UAV, a bit to the left, a bit to the right, and the absolute power is some sort of indication of the range from the insect. So the idea here is that live insects are a huge risk to our forestry industry. If a shipment of timber turns up in a foreign port with live insects. It's a big issue, and that's why they use a lot of poison ports at the moment to fumigate timber. These insects get into dead timber, so if you fell an area of timber and you leave trunks and stuff there, the insects will get there, and then the question is, if you next week fell something over the other side of the hill, how long does it take the insects to get from the rotten timber over to the timber you've just felled when you're about to take off to port? So it's about, oh, and the other aspect of these insects is they are cannibals. So normally the way entomologists work is release and trap. So they'll release 1,000 insects, they'll have traps scattered around at different ranges, and then they'll see how many they capture at different ranges and then get an idea of dispersal. The problem with these insects, you put 1,000 of them in a box, you go to release them and you've got only a few left. So the idea is that instead you tag individual insects, and you can get incredibly small radio transmitters. Sort of the electronics is the size of a large grain of rice. It uses a battery that's designed for hearing aids, and a tiny little sort of filament wire as an antenna, maybe an inch or two long. And they last about 48 hours, just putting out pings every now and again, and they're the things that we're tracking using this. And the other approach we took, because this is done in collaboration, co-supervised by the student project, co-supervised, final year project, co-supervised by Richard Green, computer science, computer vision. That because these insects move about when it starts getting a bit dark, you paint the insects with the back of the insects with a retroreflective paint, and then use infrared illumination, and you chase the spot with an infrared camera. You remove filters or get on the cameras to open up the infrared, and so you chase the bright spot. I did mention we did this in forest, but actually that's a bit of a lie. That would be ideal if we could do it in forest. We're doing this across open spaces, felled areas of forest, because it would be too difficult at this point in time to include avoiding trees. Now, what we're working on now with Scion is, and some of you might know the scientists in Scion I'm talking about here, Steve Paulson, who's a really good guy to collaborate with. Michael Hayes, I think, does a fair bit of work with Steve also. The future is harmonic radar. So this is the same principle that your avalanche tags work. The Reco market avalanche tags, you see in ski clothing, and you can buy them and stick on your boots and helmets and stuff. And the idea is that they have two antennas at two resonant frequencies, a fundamental and the second harmonic, with a nonlinear element between them. So it absorbs energy at the fundamental. The nonlinear element does a halfway rectification, so you generate a lot of harmonics, and then it re-radiates at the second harmonic. So you send out high energy pulses of signal, and normally with a radar you then get a lot of clutter because everything reflects that signal back at that same frequency. Harmonic radar, you listen at the second harmonic, and the only thing in principle that should be reflecting back at the second harmonic is the thing you tag. So we're trying to build very, very small tags, go down to much smaller frequencies. The Reco tags operate at 900, 1800 megahertz, and they're 4 or 5 centimeters long. We're trying to shrink that down to sort of 10 to 20 gigahertz, give or take, and try to make devices that are just, say, 3 or 4 millimeters, little patch antennas, 3 or 4 millimeters long. They don't need a battery, so we hope to get them small and large enough that we can stick them on an insect and use that for insect tracking. And the idea there is to be what's known as a bistatic radar, where we have one transmitter from a UAV, and we'd have multiple receivers and other UAVs, and we use multilateration by ranging to the multiple UAVs, and so the UAVs would move as a constellation, as a formation, as the insect moves about. There's a very important biosecurity application for that, which is a little different than what I described before, but it is all about protecting our forestry industry. Okay, one of the other things we're using UAVs for is climate change research, working with Gateway Antarctica. So this uses electromagnetic radiation and LiDAR measurements off a UAV. This is the way they were doing it a few years ago. They had this huge, well, relatively large instrument here tethered to a helicopter, and this is the sort of thing it was doing. It's sending high energy electromagnetic pulses down into the ice, and that penetrates through the ice, creates eddy currents in the liquid just underneath the ice, which re-radiates back, and you measure the secondary electromagnetic field and the time difference between them. Give you that range. You can use a LiDAR to measure the top of the snow. The thing I haven't shown you is the complication. Actually, you're not interested in snow, you're actually interested in the sea ice, so that's something that is they're still working on. But we have worked with Antarctica and also people out at Lincoln on shrinking this instrument down to something about this size. And this is a larger UAV. This is an 8-rotor UAV. And if you walk through the new science building and have a look through the, all the labs there now have windows, so you can see what everyone's doing. But if you look into Paul Billing's lab on the right-hand side as you walk through, you'll see 2 of these now, these 8 rotors. So they can lift much heavier weights than our quad rotors. So this is doing a similar thing to what I described here. And it's so they're taking that down to Antarctica this season to do more sea ice measurement thicknesses. Motivation here is climate change research. The extent of the ice shelf has grown, however, they feel that the depth has shrunk and hence the overall volume of ice is decreasing, but they don't have extensive surveys to back this up, longitudinal measurements. So the idea is to build up a database and compared to this, a UAV will obviously be much cheaper, much safer, and also aircraft have quite tight operational restrictions across Antarctica. They can't go very far away from solid ground, so UAVs will be a bit more flexible in order to survey larger areas. Some of the other work that's happening in the university that not so much directly with us, although this first one was us. This is more of a geospatial application here, which is measuring the edge of forests. As contractors go in and clear forests, they kind of keep tally of how many tonnes of timber they took, and they get paid based upon that. And so you want to be able to monitor these operations, and rather than having to go around and measure the edge of the forest manually, the idea here is you just put up a UAV and you use computer vision to detect the edge of the forest. It just flies along the detected edge, and it can tell you over the last week or 2 weeks, since you last surveyed it, how much the contractor has cleared of the forest. So that work was coordinated by Departmental, many of you would know. Richard Green's doing some pretty way out stuff. You may already know he's armoured UAVs with very powerful sectors and let them loose in the forest and go pruning. And remarkably, that project he's actually got the UAV now cutting branches off trees, which is pretty impressive. So that's some of the other stuff we're doing with our UAVs. Back more into a comms theme, and sort of starting to work towards a search and rescue is we've made numerous submissions to ENVI over the last couple of years. Unfortunately, we haven't quite cracked it yet on using networks of UAVs to enable beyond visual line of sight operations. Beyond visual line of sight is another one of those big enabling technologies. The Civil Aviation Authority is very keen to see technologies demonstrated that allow safe operation of UAVs beyond visual line of sight before they'll allow it. So at the moment, the regulations are very strict. You've got to have either the controller's got to be able, the pilot's got to be able to see the UAV, or you've got to have a spotter out there. So the idea is that in remote situations where maybe you're doing search and rescue over a hill, or maybe you're doing some forestry operations, maybe Richard's over here with his pruning UAVs, and you want to be well away from those pruning UAVs. You prefer to stand on this side of the hill. But at the moment, you can't do that. So having relays to provide highly robust, so that it's fail-safe, high throughput, so you can get maybe streaming video there, so you can have a high situational awareness of what's happening over here. If you're controlling, some sort of autonomous robot over here doing a job, you may need to be able to see that with high fidelity and low latency. Again, it's a control application between the UAVs over here and the controllers over here. So that requires joint optimization of both the flight planning, flight control, and the communication in order to maintain all those links. things like, for example, if the UAV in the middle here is running out of batteries, then you've got to be able to fly another UAV to replace it while that one returns to base to get charged, and keep the communication link going the whole time. Aerial communication networks. So we are working with an equipment vendor for 3G, 4G, 5G equipment, and there's an increasing interest in networks in the sky. Now, you can do that either way. You can fly a base station in the sky, which provides an area of coverage. So in a disaster situation where your terrestrial infrastructure is being knocked out, you can put up base stations in the sky. But what actually they're more interested in is, because every man and his dog now wants to fly a UAV, is can you actually control the UAVs from your terrestrial network? Can you get, for example, if this UAV is recording video, can you stream that video down to your terrestrial network? The problem is, putting all these terminals in the sky, unlike having mobile phones, people's hands dotted around the streets here, you're right above all the clutter. And this whole idea of a cellular network breaks down. This attenuation as you move away into the next cell, so you can reuse the frequency 2 cells across. None of that applies anymore. You don't get this sputter attenuation. So the line of sight uplink signals are received at several bases simultaneously, which causes a lot of interference. So, and the terminology does get a bit confusing because this is an uplink. In the communication sense, we're uploading, say, streaming video to the network via the space station. And as you can see, this might be the intended link, but because there's no clutter, all those other UAVs are also can be sent to that base station. So you've got a big interference problem. And the answer is, or we think the answer is, around uplink beamforming. So again, remember the uplink is from the UAVs to the base stations. So we want to optimise the signal to leakage and noise ratio. So we want to maximise the signal, which is the received power at the serving base. So for example, this UAV communicating to this base, we want to maximise that while minimising what we call the leakage, which is what we receive at the other base stations. And we can exploit the, we're going to do that jointly, to use these two UAVs to jointly beamform onto that base and steer nulls toward the other bases. And we can exploit the mobility of these UAVs to try to help that beamforming operation. Because you might have more UAVs out there, and jointly, we want to steer certain UAVs to certain base stations and certain nulls elsewhere. There's a limited number of degrees of freedom, but one extra degree of freedom we have with this mobility is that we can just tweak these UAV positions around a bit in order to get our beamforming more advantageous. So the challenge is to optimise the signal to leakage and noise ratio with respect to position and orientation of each UAV, and obviously the traditional beamforming optimisation, which is the beamforming coefficients, the phase and amplitude that you put on each antenna. The extension is to take that to MIMO, where you increase the number of antennas on each node, and then use multi-user MIMO to collectively use antennas from, say, 2 base stations in a virtual array. Many of you will probably remember Pete Smith. He's done a lot of work on the signal to leakage noise ratio on terrestrial networks. So a lot of this work has been done in our team by Adriel, and he in turn is referring back to some of Pete's previous work on this. And there's a whole bunch of assumptions we're making. We're just, for example, assuming every path is just a line of sight path, just a distant-based attenuation. It very quickly some of the maths gets very, very hairy in the environment. If you want to model the environment accurately with multipath channels and the like, it gets quite challenging. But that is, some work we're in the middle of, and it's really quite interesting, and is there's major international equipment vendors looking at solutions, trying to find solutions for this. Okay, drone to the rescue, or why they may one day save your life. So this work is based upon Zane Barker's Masters and in association with Andreas over in the Computer Science Department. So in fact they already have saved lives. Headline from the Sydney Morning Herald earlier this year, a drone responded to some stranded swimmers out in the ocean and dropped a flotation device to the swimmers until to give the lifesavers time to get out there and render assistance. This was under human control, so it's not autonomous yet, but it shows you something of the potential to work in emergency scenarios. So this is a project that we had, which was a joint work between this university and Yokohama National University. It was funded jointly by the Royal Society of New Zealand and the Japanese Society for the Promotion of Science, and it was motivated obviously by the wide-scale emergencies suffered in both locations, the earthquake and just a few months later, actually 1 month later, the tsunami and nuclear power station incident in Japan. So when you look at these scenarios, obviously there was wide-scale damage in both cases, and you have the rescuers in there amongst it, putting themselves at risk of further collapses, further aftershocks and the like, and access is quite difficult. This aerial photograph here in Japan shows all the fire trucks lined up along about the only road that still exists in this area. So clearly there's a number of issues there, and if you can have drones get in there, they have much better access and they remove humans from immediate danger. So wireless technologies are already used to detect casualties. So these are some of the systems available. This system here from JPL in the US is this big box which can look sideways into rubble and help detect if there's people in there. And this is from Germany, where they have to sort of climb up and over the rubble and point this instrument down to see if there's anyone underneath. So yes, but it still puts it's still time consuming, it's quite big and heavy, bulky equipment, and it still puts the rescue teams sort of right in the environment. So the motivation is that the immediate hours after a natural disaster are the most critical. The mortality rates go up quite rapidly as time goes on. And this is also the most, obviously the most dangerous time for search and rescue. Earthquakes is obvious with aftershocks. And now the opportunity comes about because we're all carrying more and more gadgets with wireless. So, this creates a wireless signature, if you like. So we obviously have phones, you have Bluetooth devices attached to those phones. We have fitness things such as a wireless foot pod there communicating to our phone or maybe to our wristwatch. And even more interestingly is that some of these devices tell us something about our state of health. So a Fitbit or a heart rate monitor or even implanted medical devices. So ideally, if we can tap into that, we can, from a UAV, from an aerial platform flying above this environment, we can use this to detect where casualties are, map them out, and then triage. If we can get anything about the biomedical data from the individuals, then in this sort of mock-up environment here, we've detected a bunch of casualties. So the green may say, yep, there's people there, but they're doing okay at the moment. Their vital signs are normal. The red dots may indicate, yeah, unfortunately they're not breathing anymore. We won't waste our time on them for now. And this yellow might indicate there's someone here who's in need of urgent assistance. So that's the vision, kind of what we'd like to work towards. So the challenges there are the casualty detection and localization. So detection of extremely weak wireless signals, which might be arbitrary. We're not saying that we're only going to detect Wi-Fi, we're only going to detect LTE, we're only going to detect Bluetooth. And it will be obscured by rubble over very large areas. And then the identification and the triage, which is using the wireless signature and being able to tap into some of the devices to hopefully help determine the state of health. And the vision here is it would use a software-defined radio, which would be able to reconfigure in order to demodulate whatever wireless gadgets we find out there to assist in this triage. So the detection problem basically comes down to the spectrum sensing problem. So we have two hypotheses. One, that so we've got a wireless detector on a UAV here, and the first hypothesis, the null hypothesis, is that we're just observing noise. And the other hypothesis is that we've got some signal, some structured signal with noise. So yeah, as I said, this is a problem common to cognitive radio, and there's numerous ways we could approach this. The simplest and most obvious, it would be an energy detector. So we just measure the spectrum, basically, divide the energy we observe across frequency bins, determine a background noise level, and come up with some sort of threshold which relates to our false positive probability, maybe 5%, and we just discriminate between those two hypotheses based upon the threshold. The advantage is it's very simple signal processing, and it's completely ambivalent to what the signal type and structure is. The disadvantage is it's very sensitive to this threshold measurement. And if you don't get that noise variance right, then you may miss things, or you may have a very high false probability detection. And the performance is pretty poor. A match filter approach. So you correlate the sampled signal against a template of expected signals, and you can set that threshold adaptively to come up with a constant false alarm rate. There's well-established methods to do that. The advantage is it's reasonably simple to implement. There's a bit of processing, but a match filter is pretty well understood, and it has very good performance and low signal-noise ratio. The disadvantage is you've got to know the structure of the signal in order to build the match filter. What's your template? And if you are going to be looking for a bunch of different candidate signals, then you've got to do this match filtering over every possible candidate. And so the way that we're approaching it is to just try to look for structured signals of some sort by looking at the psychostationary structure of the signal. So there's something called a spectral correlation density function, which basically noise-only signals don't exhibit any psychostationary statistical structure, but any sort of modulated signal does have some sort of psychostationary. So the advantage of this is it is highly sensitive. It's good for low signal-noise ratio. You don't need an estimate of the noise variance to test a hypothesis. You can come up with a generalised likelihood ratio test based upon the likelihood of signal being there or not being there, and it works with any structured signal, arbitrary signals. Disadvantage is it can get quite complex computationally. You've got to do lots and lots of correlations, but the good news is that there's some reduced complexity forms that give you almost as much performance, but at much reduced computational complexity. So this is just an example, a simple sine wave buried in noise. So this is the spectral correlation density function measured over a range of parameters, and you can see that this presence of this sine wave in this in the background noise is extremely obvious. So and you can just set a threshold based upon the scale here to quite reliably pick out the presence of that structured noise. And if you look a bit closer, you get different signatures based upon what structured signal is out there. So across the bottom we have 3 examples. The left-hand example, notice that the scale here is really quite small. That's just noise. Effectively there's no structure there. There is a small peak at 0, 0, but with the scale, even that peak is extremely small. Here we have the signature for QPSK, and here we have the signature for GFSK. So it's a half spectrum. So in fact, there's 4 peaks with QPSK, and this more complex structure with GFSK. So the idea here is that not only can the spectral correlation density function help us see that there's some sort of structured signal out there, but it can take that first step towards identifying what type of signal is there, which would help with this future vision of taking software-defined radio and reconfiguring it in order to detect the signal that's there. And so this is possible future work. Zane's finished his master's now. He's off teaching English and Japanese for a year. So I was kind of looking for other students to kind of pick up this work and go on. And we're still talking to our colleagues in Japan. I hope to get some more collaboration happening there. But the next step would be to take a software-defined radio, and this is what we're looking at. It's a Lime SDR Mini, which was just released on Kickstarter about less than a year ago. If people are familiar with USRPs, it's got about half the sample rate of a 200 series USRP, and it packs a pretty decent punch for the size. And of course, the advantage of a little thing like this, it just needs two antennas there. One's receive, one transmit antenna if you want to transmit from it. Very good for mounting on a UAV. Very small and compact, with just power directly off the USB there. So this is the sort of thing we'd like to put on our UAV. So you can use tools such as GNU Radio, and for example, configure GNU Radio to do that cyclostationary test, the cyclocorrelation density function, and also reconfigure it to detect, for example, an 802.11g Wi-Fi signal, which is something we can easily generate and take out to the field and test. And another aspect is the flight planning. So what this little animation tries to illustrate here is you have this black dot, which might be our UAV with our detector on it, flying over this area. However, not all these transmitters will be transmitting 100% of the time. They all have some sort of duty cycle. So there's an optimization to be done here is about how fast you should fly, what pitch you should fly, what path you should fly across this area in order to maximise the likelihood that you'll find all these random transmitters, random in location, and also, as far as we're concerned, random in terms of when they're transmitting, when they're not, in order to maximise the likelihood of finding them. And then ultimately we'd like to extend that to where we have multiple UAVs operating. So how the UAVs, how the swarm can collaborate, and it won't necessarily just be a simple environment here where you fly sort of stripes backs and forwards. There may be landforms, there may be buildings, there may be areas which are quick to cover, areas which are slow to cover. So doing that flight planning in order to maximise the likelihood of finding casualties. So Andreas and I are supervising a computer science student doing a PhD in this area at the moment. The Japanese side of the project was looking at the localization problem. If you get a sniff of something being out there, how do you pinpoint that? So they were working on ultra-wideband techniques in order to very accurately pinpoint. So this is them working in their office over in Tokyo, or Yokohama actually, and then they came out here and we did some joint flight testing out in Island Fields. And that was a joint team a year and a half ago out on Island Fields on a lovely day, probably a bit like today. And I'll just leave you with some nice little video that from last season down in Antarctica, which was the first flight of, hopefully that runs. Don't know why that's not running. Maybe we won't get to see that, which is a shame because it's the most interesting part is towards the end. Yeah, that was the first flight of that electromagnetic measurement of the sea ice thickness of last season, and it's going down again with some enhancements in a couple of months.
Can you get the source file? Just play the source file.
Yeah, I could try to find that, yeah. While I try to find that, if anyone, that's the end of the presentation, so I'm happy to start taking questions or comments.
That particular UAV that Graeme is referring to will sail aboard a sea icebreaker ship from South Africa, and it will take a journey towards Antarctica. They will make many stops and they'll take many measurements. We were short of manpower. We needed to find someone from geography. That's why Paul Beeling has our UAV. And just because while you're out there, you need to have a lot of backup. They have replicated, because that 8-rotor UAV was the one that we built in-house. They've replicated it now with the instructions that we gave them. They've created a second one just in case.
I don't know why this worked last Friday on this computer. For some reason, it's yeah. All right.
I'm not familiar with the RECO system. What limits the size of the? Have you got any idea in terms of the miniaturization of the?
Yeah, I mean, it's largely to do with the antenna size, which is to do with the frequency, right? So I think the RECO is about 1/8 wavelength, lambda on 8.
3 millimeters long, isn't it?
No, they're about 4 or 5 centimeters long, because the fundamental there is 900 megahertz. So we're going up to about 10 times the frequency. So we hope to be able to shrink the antennas down to about 1/10, so maybe about 4 millimeters. Yeah.
I was just thinking if there's anything downstairs in terms of making small antennas and electrodes and diodes.
That'd be great. Yeah, we've actually been picking Kim Eccleston's brain a little bit. He's been quite helpful with getting one of our students up to speed on microwave office. So we've got some designs. We've simulated designs now, but we haven't actually looked at how we fab them yet.
Well,
Yeah.
it's, materials and thin film.
Great. I'll be knocking on your door. Yeah.
I remember helping to examine a project a few years ago with those Yagi
Right. Yeah.
antenna, and I couldn't get my head why, when you've got a rice, something the size of a rice grain, I know the antenna's a bit bigger than why you need such a big antenna. It always seems a bit out of. You'd think that the two things could be possibly done with something along the same size.
Yes. Yeah, that was. I think the frequency is somewhere around 450 megahertz. I can't remember where the ISM band there. So I think that the antenna on that was certainly wasn't halfway, but probably it was, I don't know, 8th or 16th. It was so yeah, I mean, I'm not an antenna expert. Kelvin was the guy that built those Yagis. But yeah, I think the Yagis are probably indicative of the wavelength that was being used, and the tiny little transmitter was using a smaller than an ideal antenna, but simply because it had to be small.
Still significant in size to the insect, though.
Yes, yeah, but it was a filament. It was like you could barely see. You had to hold up to the light to actually see the wire. But yeah, it was 3-4 centimeters long maximum. Yeah.
Slowing down the distance of the spreading of the.
Yes, yeah. Well, the insects that were being tracked were relatively large. I can't remember the names of the insects, but the insects themselves were only 2 centimeters long. So the rule of thumb that Steve Paulson, the entomologist, said is about 1/10 of the body weight. The insects are capable of carrying about 1/10 of the body weight.
How does that compare to a drone? What's the payload of a drone compared to it?
That's a good question. I don't know the ratio, but certainly flight time and payload inversely. So our aeronautics craft can fly maybe up to half an hour if you stretch it, if they're completely without anything on them. But you load up those Yagis and stuff, then you might only get 15 minutes out of it. Yeah. I don't know. Can anyone want to hazard a guess how heavy our?
It's just got so many variables.
Yeah, but about the maximum payload we can carry is about 2 kilos. That's probably pushing it a bit. So maybe a kilo and a half.
Well, I mean, that 8-rotor one can take up to 8 kilograms of payload.
Yeah.
But it is, if you don't really put a lot of sensors on it, so when you talk about payload, it's like that thing. So if you want to have greater duration of flight time and you add batteries, it's not that when you add a second battery you get twice that, because the battery itself is also heavy. That's the point. But that's a good question. I don't think I've ever heard or we've ever sort of tried to find a ratio between the weight.
I'd say our aeronautics, which is maybe 1.5–2 kilos load, probably be no more than 5 kilos, including the battery.
4 kilos. You mean payload?
No, I'm not talking payload. I'm talking about the weight of the craft,
yeah.
to get the ratio of the craft to the payload. Yeah.
The rocket's about 2%.
2%. Wow. And most of the weight would be fuel, I guess, which you just blow up in a matter of seconds.
Well, I guess a bit of takeoff, but fixed wing gliders, they're far more efficient than Sky a lot.
Yes.
But I guess you've got a minimum speed. How many of these applications could you go to?
That's an excellent point, and that's exactly where we're going with the Antarctic one, which I can't show you here. We've got a master's student working on trying to develop a relay system whereby to get greater range, and also with greater range we actually do want to be able to move more quickly. So the concept we have there is that the instrument will be on a fixed wing aircraft way out there, but we may have some aircraft in the middle which may be multi-rotor or may be fixed wing in order to form a communication relay. But yeah, for this we want to survey large areas, so as long as we can fly slow enough that we can get reliable measurements, then doing the survey of a fixed wing is where we're headed.
It's kind of a silly question, but I'm kind of a bit confused with the whole safety aspect of having one of these crafts in sight. I mean, I understand the idea that you have to have them under control, but things can go wrong even if you have them in sight. You could imagine that a craft goes haywire and you can't stop it even if you can see it. So
Yeah.
I don't know what the reasoning is behind that.
Well, I think the expectation is that if you can see something going wrong, then you have the ability to land it. That's not always true. In fact, we had an incident, thankfully not our project, but we happened to be in the field at the time, out on Island Fields here, where the IMU, the inertial measurement unit on the UAV, was actually not properly attached to the UAV, so it was rattling about. And thankfully it was only a small UAV too. And it took off at great speed across Island Road and crashed on this side of Island Road.
Into the registry building?
No, it was getting there though.
Yeah. On the window?
That was a bit of a wake-up call, that one. That was a very early prototype for the craft that Richard is now using in his pruning stages as well. He didn't have these secateurs attached. And that was as simple as not having the right double-sided tape or Velcro or whatever to hold the IMU. So even though it was well within visual line of sight, it's still a hazard.
That harmonic radar, is that passive? I mean,
Passive. Yeah.
Oh, I've never heard of that.
Yeah.
All the European ski pads.
So you basically have an antenna that receives a fundamental, and you have some non-linear device, which is just a Zener diode, and then you have an antenna that is resonant with the second harmonic. So I mean, the loss in the system is quite big, 20 or 30 dB. Passive.
Well, it's time for coffee, isn't it? That's all it is.
Right.
Brilliant. Thanks a lot, Grace.
Thank you.
Yeah.